Now that we know about Gauss integration, we can proceed to the isoparametric element concept. This is an element family that is developed by mapping. And what is done is that the original shape of the element, which might be rather arbitrary, is mapped onto a more perfect shape. Sometimes that's called a parent element. And the parent element might be a double unit line element in one dimension, or a square in 2 dimensions, or a cube in 3 dimensions. The reason that you want to map the original physical element into a more regular parent element is that the integrations that are needed are much more easy. And in fact, then the Gauss integration formulae can be applied directly. Now, the method works best for the so-called elasticity elements in 1, 2, and 3 dimensions. In fact, there was at one time a whole code that was based just on isoparametric elements. It was called Superb, written by Structural Dynamics Research Corporation. It's not separately on the market now, but it shows the interest in this kind of element. I think today it's become one of several classes of element. The mapping technology is unique and very interesting. It does remind me a little bit of the conformal mapping used in aeronautics, wherein a Kutta-Joukowsky airfoil was mapped onto a circle, and then it was found possible to satisfy the boundary conditions for the flow over that airfoil and get the lift. Our approach here is to first describe the independent variable interpolation, in other words, this mapping. Then next we will talk about a line element that's isoparametric, then about a quadrilateral element that's isoparametric, and lastly we'll do several problems. The mapping procedure that we use in isoparametric elements is a unique piece of technology. Let's review first what we did on the evaluation of the dependent variable f of x, and then we'll return to the evaluation of the independent variable later. I'd like to review what we discussed earlier. I've pointed out that when we're trying to find an intermediate value of a function where the endpoints are known, we actually prefer to do something that is really extrapolation, namely to take the value, say, at the left end of the interval, multiply the slope of the function, and then take the difference out to the position at which we're interested, which would be this. And if you do a differencing of that term here, which is the slope term, then the whole expression becomes a function of the endpoints as well as the interior point, and we don't need the derivative. I feel that this form of the expression is fairly intuitive for engineers and does correspond with the way that we estimate position on mountain trails looking ahead toward some objective point in the distance. If we now collect the polynomial terms that multiply the functional values at the endpoints, then we get the useful interpolation form shown here. The endpoint evaluations are underlined here, and then the collected groups of polynomial terms are called the shape functions, which indeed they are. And we arrive at the form in this equation, which would indeed be exact if you were lucky enough to be interpolating a linear polynomial, shown in red below. The process then is to multiply the left functional value here by the shape function at whatever point you are interested. Let's say here at x, and then multiply the right functional value times the shape function n2 at that value, and then that will give you the interpolated value for the function of x. Now we're going to change gears and talk about interpolating the independent variable. And this is not very intuitive because we're more used to looking for values of a function over some domain. But you see, when we get into the mapping, we're actually stretching and distorting the domain itself. So we need to get something akin to an interpolation of the independent variable. I start out with the outrageous idea of interpolating x in terms of the endpoints x1 and x2. So we're trying to find the location x of a point interior to this element lying on a straight line. And we use the shape functions n1 and n2. Now, we can use, it turns out, the same shape functions that we did for interpolating the dependent variable. And I'll put those in here. Now, this seems pretty strange and a crazy way to do things. Let's first, though, just show that it makes some sense, namely that if you take these terms and simplify, multiply out and put it over a common denominator, you get a lot of cancellation of terms here. These terms cancel, these terms cancel. You're left with x times x2 minus x1 over x2 minus x1, and ta-da, we get x equals x. So it's hard to claim that's earth-shaking, but the idea generalizes and is particularly useful when you have curved lines and then distorted 2- and 3-dimensional bodies that need to be mapped. This procedure of interpolating the independent variable actually is very important for our mapping process. In our case, we found something trivial, namely x equals x, but that's actually legitimate, and later we're going to find when there are several sets of independent coordinates that then you get a relation that actually allows you to deal with curved bodies, curved sides of elements. In our particular case, when we use the same shape functions for the independent variable as we did for the dependent variable, that's called isoparametric because we've parameterized the mapping with the same level of accuracy for the boundary of the element as we did for the interior on interpolating the dependent variable. And iso, of course, meaning the same. I think you're familiar with isoclines and other curves that represent something like that, but this is isoparametric. Now you can also get superparametric elements where you do a better job on the geometry, which is the mapping of the independent variable, than you did on mapping the field variable, which is the dependent variable. So interestingly, it's the boundaries that are used as the reference here as the dominant mapping. The subparametric case then would be where the geometry might be mapped with less accuracy than the field variable. Now, a common case that could happen here, let's think about this. Plate elements and shell elements are one where people at times will decide that the field variable through the thickness might only need to have a linear interpolation, and yet the boundary, the element itself, might have some curvature through the thickness, and so you can get superparametric elements in that case. It would require some simplification in the field variable in one direction in order for that to happen. But I would say both superparametric and subparametric elements are not very dominant. A simple example for us will be the line element, and I will take a line element defined on the x-axis and map it onto the z-axis. So this will take our physical space on the left here and map it onto a double unit line over here in the z space, and this is called the parent element over there. So mathematically you can show that this set of points from x1 to x2 is mapped onto a set of points from -1 to 1. Now that mapping, if we do it just by inspection, will lead to these shape functions. rather than labor on that, let's just check and make sure that it's true. For instance, the point here at -1 in the xy plane would give us 1 minus 1 over here, which would give 2 in the numerator, which would cancel the 2 in the denominator and lead to the term x1 here. And here you would cancel out, and therefore you'd get x equals x1 on this diagram corresponds to the xy equals 1 that we talked about here. And you can show that the right end also transforms properly. Then points in the interior are translated and stretched in a linear way because these are linear shape functions and give a linear mapping. Not only then can you do the independent variable, but you can interpolate the dependent variable shown here with the same shape functions, and therefore we are in the process of developing an isoparametric element. Let's consider how the integration for the stiffness will change as we move from the x-coordinate to the xy coordinate. The physical integration is shown first and involves limits, it involves an integrand, and it involves the differential quantity on x. Now to change our variable of integration, we have to change the limits over to those for the new domain without changing physically what that domain is. We need to replace the integrand's dependence on x with the dependence on xy, so that's a direct substitution of variables. Then the differential quantity dx is replaced by the Jacobian determinant times the dxy quantity. Now you might wonder, why would that be? Well, we can argue that in one dimension pretty easily, and in fact infer that the Jacobian is dx by dxy merely by writing out the differential quantity dx and setting it equal to dx dxy times dxy, and you can see where the Jacobian comes in. We can also evaluate that by going back to our shape function form, and when that's cleared of terms, you end up with this numerator here that turns out to be the original length of the physical element, and that's compared with the length of the parent element, which is 2. So the Jacobian in this case turns out to be a length ratio. Now the integrand also contains a material law, which for our case is just Young's modulus, which is a constant. The strain displacement law, however, has a derivative, and that we must change over to a derivative on xy. And we do that with the law d by dxy times dxy dx. And this we know how to do. That will also give us a length ratio. It'll be a reciprocal ratio. And we end up then with a derivative on the xy variable. An important part of the stiffness calculation is the shape function matrix. I show that here. Then we can find the strain matrix B as the strain displacement law times the shape function. That's going to involve that derivative that we just dealt with, and then the two shape functions here. Those derivatives are easy to take. You get a unit value. Of course, you get a -1 here and a +1 here that gives us this result. So in fact then, on the matrix B transpose, then the material property G, and then the B times the determinant of the Jacobian times the cross-sectional area, which was a placid quantity here in our calculation and factors out, and then the dxy, you find that you have a constant integrand here and corresponding to our constant strain element, and you factor out the EA over L, and you'll get the same matrix that we got by classical integration in physical coordinates. So this just shows then that there's an alternate way to calculate the line element through this mapping procedure. And of course it's not needed here because we could do it in physical coordinates. But there are many problems where these mapped coordinates are far more easy to do the problem. So let's move to a more complicated example. This will be the quadrilateral using plane stress. So I show a four-noded element embedded in the XY physical plane, and overlaying is the xi eta coordinate system, which are these mapped coordinates. The element is a straight-sided element because of the fact that we only have the corner nodes, and one can generalize this to curve-sided elements by having 3 nodes per side. The shape functions that we'll use here are sometimes called bilinear because they're linear in both xi and eta, although in fact there's a quadratic essence to that mapping. Our job this time will be quite a bit tougher than for the line element. Each of the mappings involved will have more terms. For instance, here's our K matrix in physical coordinates, and we'll need to develop the B matrix, which I've expanded here as the strain displacement law times the shape function matrix. Now the material law is not difficult in plane stress, that's universal. The strain displacement law D is universal, also coming from two-dimensional elasticity, involving the 2 direct strains and then the shearing strain definition. Now we're using the engineering definition of shearing strain here. Now we need to work out the details of the mapping itself. We want to map this general quadrilateral on the left into the double unit square on the right. There are 4 nodes, and therefore we're going to need 4 terms in the expansion. We can think of x and y separately. Think of interpolating x, the x position at an arbitrary point in the interior of the body, as a function of the nodal x positions, but we write the shape functions out in terms of xi and eta. That may look mysterious now, but it's the proper way to proceed and to allow the integration to go forward. So we interpolate y in the same manner and then show the results in summation form for both x and y. This really follows the same pattern as our interpolation of the dependent variables that we've done many times already. Well, we need to derive the shape functions, and these are going to be particularly nice in terms of xi and eta because they're going to be evaluated at the nodes in the parent element in the xi eta plane. And so, for instance, for the first shape function, which would correspond to the lower left node in the xi eta plane, the shape function should take a unit value over that home node, -1, -1, and then it should take 0 values at the other nodes that are around the periphery. I've sketched the first shape function, and it would be a surface such as shown. Now, this would be apparently linear in the coordinate directions, but actually is a curved surface, as you can see. I've drawn this line from opposite node over here to opposite node here to show the general curve shape. We will use a product form in developing our shape functions involving a constant, and then fairly easy to identify the 1 minus xi and 1 minus eta quantities. In the xi eta plane then, if I sketch it here, what we've done basically is bake in the zero crossing on the upper and on the right hand boundaries, and that will ensure that the grids at this point and then at the two outside points over on the right are going to be 0. Well, when you evaluate the constant at the home node, you find that you get 2 and 2 for the functional evaluation of this product, and the constant has to be 1/4. We put that in. Now, we've gone through quite a few of these shape functions before, so I'm just going to summarize the information in the next figure. Here's the matrix of shape functions. I've carried N1, the first shape function, in the position to help interpolate for x. That same function helps interpolate y, of course, and multiplies the y1 coordinate. Then we have the N2 shape function, the N3, and the N4. So you can pick up one of each there. Now, these are called the serendipity shape functions, and named after the princes of Serendip, the island which is now called Sri Lanka. And of course, they were the princes that always had great luck, and no matter how they goofed off, they always came out smelling like a rose. So these are, in the same way, are lucky guesses for us. Now, because this is going to be an isoparametric element, we're going to interpolate the dependent field variables with the same shape functions. Our goal really is to convert the stiffness matrix from physical coordinates into these mapped coordinates xi and eta. So I show the original physical matrix above, and then I show the mapping coordinates down below, the xi and eta coordinates. And the Jacobian now is given and involves the derivatives of that mapping operation. We need both derivatives on x and on y to help interpret these strain matrices here as expanded on the right, showing that the strain displacement law is going to have some derivatives in it. And we get those as shown here, and these come from our mapping. In fact, we can convert this over because because of our shape functions, we're going to be able to actually evaluate these terms that I'm circling. So the problem now is being reduced to practice. Our procedure also requires the evaluation of these derivatives by the xi and eta coordinates. And after expanding that out, shown on the right here, we can also write that in terms of the shape functions over here. This is a little bit mathematical, so I think you may need to stop and just look at it a little bit on the side. But certainly now we're involved in getting derivatives of shape functions. So now we know the terms that are involved in this expression. We recognize this matrix here as the Jacobian. And if your mapping is a good one, you can invert that relation. This is sometimes a source of trouble in finite element codes, and you'll find that the Jacobian does not work in codes if you distort the elements too much, so that the inverse doesn't exist over the face of the element. But we'll assume that it does exist and then invert that relation as shown below. I feel a little bit like a used car salesman, and as if I'm putting things over on people. The previous equations were all pretty dry mathematical, but here we're going to put them into practice in the integral for stiffness. So I show the complete expression here. It's got the terms that involve the shape function and their derivatives. Let's see here. It's got the derivative terms are appearing back in this operator here that was the strain displacement law. And then this is the shape function matrix. Here's the Jacobian, the determinant Jacobian, and we've changed the limits on the integral now to coincide with the C eta coordinates. The thickness h pops out of the volume integral outside the integral. Now, one thing that's fun, and I've tried to do, and it's kind of a problem to track the polynomial degree, but g would typically be not a function of space for a uniform material. These derivatives here end up being linear in C when you take derivatives of the shape function terms because they're quadratic, you know, this so-called bilinear form. You've got inverse terms on the Jacobian, which will involve some polynomials of C and eta in the denominator. So although this is a little fragmented, we are going to end up here with at least linear terms in the numerator here. The Jacobian is going to end up with at least linear terms in the numerator, but I should say each of the Jacobian terms is linear, so this could be actually quadratic. And so we're ending up, at least in the numerator, with what would be at least linear, quadratic. It's at least a fourth degree polynomial in C and eta. Now your integration scheme with Gauss integration should account for the details of this. Usually it's under-integrated. In other words, we don't do an exact job on this because normally you're trying to evaluate a polynomial, and this might even be a rational function of C and eta. It would be a ratio of polynomial terms. So we don't expect the Gauss integration to be exact, and that's not the goal. In fact, there are some elements that turn out to be too stiff when you integrate them too thoroughly with enough Gauss points, and therefore it's often felt in shell theories especially that it's better to do a little coarser job of the integration and not overestimate this stiffness. It's felt consistent with the four-noded quadrilateral to use a Gauss point integration pattern that's 2 by 2. I show that here, and these might be the Gauss points, for instance. What you're really trying to do, though, is evaluate a surface which is shown to the right here, which is the red crosshatched surface. And so by only sampling at those 4 points, there will be some integration error involved. Our first problem on isoparametric elements has to do with some details about a rectangular element. This is meant to be a two-dimensional, perhaps plane stress element, to be mapped, of course, onto a double unit square. Two questions involved about the process are, to what point xy does this C eta point correspond? So we need to find the mapping involved in order to take this red point here and map it over into the xy plane. Secondly, what is the value of the determinant of the Jacobian? Maybe it would be good, while we're still looking at this figure, to give a shortcut for part B, namely that we know that the Jacobian determinant is equal to the old area over the new area, so it's an area ratio. Now, the body on the left, the physical body, has an area of 12 units, since it's 6 units high and 2 units wide. The body on the right has only 4 units, so that ratio of areas is 3. So we'll see whether that's brought about in the calculation that we will also do. But that particular question, part B, could be answered by inspection. The solution to part A of our question has to do with mapping from the parent element back to the physical coordinates. Our general mapping relation is shown here and makes use of the shape functions, and the shape functions are written in terms of xi and eta. Y is likewise interpolated with the same shape functions. Of course, the independent variable x is going to depend on the nodal values of x. The independent variable y is going to depend on the nodal values of y. Alright, so if we write out the description here with our serendipity shape functions that we developed earlier, we have these 4 shape functions involved. What we need to do then to evaluate at a specific point, for instance for x, is to put in the value for xi here and the value for eta here, and that appears in this location, and so on. Then we need to put in the x coordinates of the 4 nodes in turn. When you turn the crank, you find out that the x coordinate corresponding to xi of 0.5 is also 0.5. This is because there isn't any stretching in the x direction. In fact, x and xi map on each other one-to-one without any stretching or translation. So finding the x-coordinate turned out not to be difficult. The y-coordinate will involve some stretching, so we'll check it next. Again, we expand the general y independent variable in terms of the shape functions and in the y nodal values. If we want to do the mapping then from the point in the parent element at 0.5, 0.2, we put those values in again as we did before, and then include the y coordinates of the 4 nodes. Turn the crank and you come out this time with 0.6. So that number would have been a little more difficult to guess. I show at the right here how that point does map over into the xy plane. So there's no stretching in the x direction nor translation, but there is stretching in the y xi variables. Part B of our question had to do with the value of the determinant of the Jacobian. And as I'd said, we could get that by inspection. If we just calculate the ratio of areas, we would find that it should be 3. But let's also do the calculation in a formal way shown here. We need to evaluate the various derivatives involved. They in turn depend on derivatives of the shape functions. Normally one would expect the derivatives involved to be polynomial functions of xi and eta, but in this case they will turn out to be constants. We wouldn't know that ahead of time, but if we put in now the positions of the nodes given by the x sub I terms here in this expression, we then would have the possibility to calculate this first derivative, and there's a lot of cancellation involved. You see that there's here a minus eta, which is going to cancel a plus eta, let's say over here, and then here's another minus eta that will cancel a plus eta over here. The remaining terms sum to unity. Then we can take the derivative of y by xi, and putting in the y nodal points, we would get this expression, and again a cancellation of the eta terms and yields 0. Now we have 2 more derivatives to evaluate. Let's take the derivatives with respect to eta. And when we do that expansion, we evaluate at the nodal x values for the x derivative, and that turns out to be 0. Finally, when we look for the derivative of y by eta and expand that out, and then if we put in the proper values for the y's here, we'll find that we get 3. When we put these into the Jacobian and we take the determinant, we have a unit value and then 3 and 0 on the off diagonals, and we get the final answer that the determinant of the Jacobian is 3. And this does agree with our previous concept of the area ratio. Problem 2 deals with an 8-noded quadrilateral. This problem is useful because it makes us start to think about elements that could have curved sides. The questions are going to be posed, though, in terms of the parent element in the xi eta plane, where it's a double unit square. The first question has to do with the possibility of a displacement function that would have the following form, and the question is it suitable to have such a form? It's a cubic polynomial with 10 generalized coordinates. Part B of our question has to do with a discussion of the shape functions. We're to describe the serendipity shape functions for this quadrilateral, and it's stated that the functions need only be cubic, no higher. Now, in our solution to part A, we immediately recognize that there are 10 generalized coordinates given, but yet we really only need 8 present because there are only 8 nodes. So in order to achieve the balance between the number of unknowns and knowns in a problem such as this, we need to drop out 2 terms in that displacement function. We could, for instance, drop out Q6 and Q9, or alternatively Q7 and Q8, and that would preserve the geometric isotropy of the system. Okay, for part B, we would consider a mid-side node case, let's say here, by saying that we could take the product of the lines passing through the right boundary of the element, the top of the element, and the bottom of the element. The product form then of the equations for those 3 lines will guarantee that the function involved would be 0 at every node on those 3 boundaries. I'll sketch the figure again here and give the equations along those boundaries. For instance, on the right side, c minus 1 is 0. At the upper boundary, you'd have eta minus 1 is 0. At the bottom boundary, eta plus 1 is 0. So we combine those factors up above into a shape function with a multiplicative constant c that will scale it. And then when you evaluate that at the home node, you find that the constant is 1/2. You can do a similar thing for the shape functions that have home nodes at the vertices. For instance, n7, which would have the home node here. That would involve the product of the lines passing through this diagonal line here, given as this equation, plus the right-handed equation here, plus the bottom equation. And that product leads to this form where the constant has been evaluated at 1/2 also. So you can see how this could go for any of the other nodes. Problem 3 deals with a parabolic line element. Here we're talking about a special situation where we have a physical element on the left which has 3 unevenly spaced nodes. Of course, that will be mapped onto the double unit line in the xi coordinate axis, and the center node will lie precisely at the origin here. So there is some unusual stretching involved in the interior of the element in this mapping. The first question, that is part A, says to find the mapping that does this job, and then part B says what is the physical coordinate x1 that corresponds to the Gauss point C1 on the right side here. Now for that we'll have to look up the classical Gauss point on a two-point integration. The first part of our solution is primarily a problem of finding the shape functions that will help us do the mapping. We know the general form of the mapping is like this, and this is the interpolation of the x-coordinate, which is the independent coordinate. Now the quadratic shape functions can be found as sketched here in the figure at the right, and they're given here in equation form with their constants determined. They're color-coded so you can identify which is which. Those shape functions then will directly give us our mapping. We just enter those in the proper location here. To complete it, we really should put in the numerical values for the positions of the nodes in the x-coordinates. This would be unity. This one here would be 2.4. And this one here would be 3. So that finishes our mapping. Then in part B, we're asked to evaluate a point that originally was called C1 here, the first Gauss point in the C domain, and find out how that can map over into the physical domain. To get that, we look up the tabular value, which for the first Gauss point is 0.5773, and we put that into every spot that's needed in this equation. When you evaluate that, you get 2.844, and that's located at this point here in the physical domain. So that completes our problem on the parabolic line element.